like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks. I'm an associate professor at the University of Utah, and I'm joined, as always, by my co-host, Andrew Falkowski. Andrew, how you doing?
I'm really tired, but it's good to be here. How about you?
You just got back from New Zealand, is that right?
Yes.
Man, and people thought I was the world traveler. How was that?
It was fun. It was a good time. It was a very short trip. I found some nice flights. Very interesting country. Not exactly what I had expected. It kind of reminded me of America maybe 20, 30 years ago. I wasn't alive then, but that's kind of just what I'm postulating.
Okay. How about this? Is it a place that you feel like you have to go back to?
Yeah, I mean, I was only there for like 3.5 days, so, I mean, how much can you really experience?
Geez, you spent as much time traveling as you did actually being there, I feel like.
Yeah.
Well, glad to have you back, man.
Yeah, what have you been up to?
Same old, same old. So I am here in England. As those who have listened the last couple episodes know, I've been on sabbatical in the UK. And so I am still here for another 6 months. It's sort of the midway point for me. And it's just been the speaking circuit to end all speaking circuits. Like every week I'm at another place giving a talk. So it's been really fun. It's been surprising how many fans we have in these random parts that'll show up to the seminar that gets promoted. That's been really cool to see.
Yeah, I'm sure that's awesome. So what are we talking about today?
Well, okay, let's set the stage. If it wasn't that long ago, it was around New Year, that the big announcement, right? People have called it one of the biggest breakthroughs in our lifetime. They're saying it's bigger than you name it, that's happened in essentially in the last generation. And that is the breakthrough over nuclear fusion. Now, from University of Utah, we have a sort of storied past where cold fusion, right, was something that Pons and Fleischmann said they achieved. And it's this whole big debacle where it didn't go through peer review, but they took it to the press. Then nobody could reproduce it. So it's been a bit of a black eye at the University of Utah. And so every time that there's an announcement out cold fusion, that comes to mind. And they do tend to get overhyped. People talk about this as the clean tech solution to energy to end all clean tech solutions, right? So when I saw the headlines about this, I was like, yeah, I guess we'll see. Well, as we dig into it, this one looks pretty legit. Now, the problem's not solved. They do always oversell it, but there's a big breakthrough in what they have achieved at Lawrence Livermore National Laboratory. So maybe to set the stage, I'll say that there's been some other breakthroughs in the last couple of years. For example, in December of 2021, the Joint European Torus jet, right? This is the Europeans that are trying to achieve fusion. They had something pretty exciting. They were able to operate their tool, this Torus, for sustained fusion for 5 seconds, and they extracted 59 megajoules of energy, which isn't like a huge amount of energy. Basically, they point out that that's enough to power a home for a day, basically. But they only burned 0.1 milligrams of tritium. So these things are crazy efficient. By the way, just to put that 59 megajoules of energy into context, that's about half of the energy that's in a gallon of gasoline. So it's not a huge amount, but the rate at which they can generate it is massive. The power output of these can be absolutely colossal. So that's pretty cool.
There's other sorts of costs that have to be factored in. I mean, the facilities themselves, at least the ones that exist right now, are quite expensive. Millions, maybe even billions of dollars.
Oh, totally. So that's the announcement that came this December. It came from Lawrence Livermore National Laboratory. Now, these two places achieved fusion in sort of totally different ways. We're going to talk about how fusion works very briefly in just a moment. But essentially, you've got to squeeze atoms together, right? It's fusion. You're causing these things to come together. And if you've taken a Gen Chem course, you know that there are Coulombic attraction if things are oppositely charged or repulsion if they're positively charged. So if you try and squeeze two nuclei, which are both positively charged together, you've got to overcome some pretty massive repulsion. And obviously the sun does this just by having ginormous gravity. It's so massive that gravity squeezes these things together. So not very efficient. The Europeans in their jet system, They use magnetic confinement. So they introduce gas and they ionize it. And when it's ionized, now a magnetic field can cause it to sort of stay ionized and sort of contained in the space. And then they heat it with radio waves, so essentially microwaves, right? And with neutrons. That's how they heat it up. And if you get it hot enough, then that's how they did it. But Lawrence Livermore does it this totally different way using, cue the audio from Austin Powers,
which was in essence a sophisticated heat beam which we called a laser. Using these lasers.
I remember I was a grad student 15 years ago when I first heard about this, that they have a whole bunch of lasers all pointing at the same spot. 192 to be precise, right? And each one of these lasers is sort of like as strong as the world's strongest lasers. So they've got all of Dr. Evil's lasers pointed in one tiny little spot, the size of like a ball bearing, like 2 millimeters big. And the supporting facilities that make this possible are pretty bonkers, right? It's as wide as, this comes from a really great article reported by Kit Chapman in Chemistry World, which we'll put in the link in the description. It's really great. But he describes it as being as wide as 3 American football fields. It's 10 stories tall. They've got over 3,000 sheets of phosphate glass doped with neodymium to sort of direct these lasers at just the right spot using just the right angle. It's this completely massive effort. And with that, they were able to achieve fusion. And here's how they did it. First off, they have a little tiny cylinder inside that all these lasers are pointing at called a Hohlraum. And our German speakers will know that that means hollow, right? And it is. It's sort of like a little cylinder. It's hollow on the inside. And floating or suspended in the center of that cylinder is the little bead of nuclear fuel. So what they do, and this is so clever, I think it's so clever, they point these lasers inside that. So you've got 192 of these things pointing inside of there. And as soon as they turn this thing on, and it's only on for picoseconds, right? Very, very short period of time, it immediately creates what they're calling a bath of X-rays, right? These lasers get in there, they produce X-rays all around your fuel sample, and all those X-rays will then immediately ablate the outer surface of your pellet. And if you ablate the outer surface, then that means that the outer surface goes flying off radially outward. And law of conservation of momentum says, okay, if something flies off outward, then you have to have the inner part of that didn't get ablated get projected inwards, right? And so it does. And that is how they achieve the high density and temperatures needed for ignition. So they actually achieve a density over 100 times the density of lead, 100 million degrees, all happening over a few picoseconds. And what's cool is if you look at the power used to do this, because it was such a short period of time, the pulse only cost about $14 in electricity. So pretty wild. And for the first time, they were able to get more energy out than they put in. So that's why it made the news, right? This is a big deal. Now, people are overselling it and saying like this problem's solved, and it's not. In order for these things to be viable, we're not going to be able to have all 192 of the world's most expensive, powerful lasers everywhere that are generating electricity. So we've got to find ways to bring the cost down, and we need to get more energy out. Ideally, we want 50 to 100x return on the power from what you put into it. And it's not there yet, but we thought that this announcement was sort of big enough that we ought to do an episode on the unsung hero of all this, the materials that make fusion possible.
Yeah, if you ever look into any of the, I don't know, pop science articles that have come out about this, it's really hard to get a gist or really kind of understand or appreciate how technically both impressive but also challenging this problem is. A lot of articles are kind of just come from a number of like science hypesters, and that, like you said, they seem to act like this problem is already solved and that we're just a few steps away. But I think that there's a lot of interesting materials challenges that maybe point to the fact that the technology isn't as ideal as we might have thought. And we thought that it was a good time to actually kind of dive in and provide a little bit of context for that.
Yep. So Andrew, teach me, how on earth does fusion actually work? What's going on there?
I think that there's quite a few other podcasts and videos and articles out there that have done a really good job of explaining this. And we'll link to a few of those, but just to provide a brief understanding, at least so that we can all be on the same page when we talk about some of the effects of fusion on material. It really comes down to 3 isotopes of hydrogen. That is protium, which is 1 proton and 1 electron. This is standard hydrogen that we think of. There's deuterium, which is 1 proton, 1 neutron, and 1 electron. This is less abundant than standard hydrogen, but sufficiently abundant that it's quite accessible. It can be found in seawater. There's trace amounts of it in the water that you're drinking. And then there's tritium, which is one proton,
Yeah.
2 neutrons, and 1 electrons. This is extremely rare. In fact, there's only about 20 kilograms in storage on Earth. And the way that it's produced and captured right now is from decaying and spent nuclear fuel in cooling pools. And so this is something that ends up being quite important for fusion reactors, and it's also quite limited, and there isn't an easy way of producing it.
So why is it so important? It has to do with the fact that when you get fusion, essentially any lighter elements that when combined together produce something lighter than what is it like I think iron or nickel is technically going to be an exothermic reaction, right? So as long as you're fusing things together to make something in the bottom half of the periodic table, you're going to get energy out. But not all these things aren't all equal, right? First off, the amount of energy that comes off is not equal, and the temperatures required to achieve it is also not equal. So the one that is deemed sort of the most appropriate because you get the most energy out of it that's useful at the lowest temperatures is adding 1 deuterium and 1 tritium to yield 1 extra neutron and your helium-4 isotope. So that neutron is what's going to be coming off of it. It's going to have 14.1 MeV. And Andrew, that's a whole lot more energy than, say, what we're getting out of the neutrons that come off of fission reactors, right?
Oh yeah, quite a bit more. And there's all sorts of other reactions too that can take place. You can combine 2 deuteriums to yield a neutron and helium-3. You could combine 2 deuteriums to also potentially yield a proton and tritium, or you can combine helium-3 and deuterium to yield a proton and helium-4. Now, not all of these emit the same amount of energy, which is kind of why there is so much interest in the deuterium and tritium reaction. There's also some interest in the helium-3 and the deuterium reaction because it has a similar amount of energy. But then you start to run into problems of the cross sections, with essentially the probability of these reactions taking place and the conditions needed to ensure that they can take place.
And if you've looked back at our episode on 46, Better Nuclear Fuel, we talked a little bit about some of the material requirements happening with fission, how inside of, say, where the fuels are housed, you have the cladding that goes around it. And these undergo pretty catastrophic conditions because you've got these big radiation influxes. They're at relatively high temperatures. So you've got corrosion, you've got formation of fissile products within the cladding that makes them prone to creep and failure. Okay, if that's all a problem with fission, with low energy neutrons coming off, then what's going to happen inside of a fusion reactor where we have neutrons coming off with far higher energy? It's going to be an even more severe material problem that we're facing.
Oh, absolutely. I mean, these plasmas are heated to billions of degrees. I mean, this is why there's so much interest in using these magnetic confinement fields, is to try to keep this
Uh-huh.
hot plasma away from the material, because obviously that's way higher than any material's melting point. If the materials were directly in contact, there's no way. But like you said, there's still neutrons coming off, which have kinetic energy. There are and a whole host of other problems.
And it's been interesting when you look at the people that have done it here, like the jet, for example, they have changed their materials components based off of what they've learned in this process, right? Here's this quote from Greg Bailey. He's one of the members of the UK Atomic Energy Authority, and he said Jet initially they changed their walls because they initially thought that they were going to make the walls out of carbon, and that would just make life easier for the experiments. It would have been perfect, but in actuality, it turned out to be terrible because they ended up with a ton of what's called tritium retention, where we were losing our fuel into the wall and the hydrogen was drifting inside the carbon. And so this sort of simplistic approach of using what they considered at the time to be the best material didn't work out at all, actually.
Yeah, anytime you have high temperature, carbon always seems to be kind of like the easy go-to, but as soon as you introduce anything like hydrogen related, it becomes a pretty big problem just due to its propensity for reaction. But let's actually dive into what this fusion environment looks like in more specifics. So I think there's a couple components, and maybe this first one is the thermal stresses that you're going to be experiencing. Now, there's estimates that some of these plasma facing components are going to be experiencing thermal fluxes up to 20 megawatts per square meter. Maybe that's more on the extreme end that's been quoted. I've also seen maybe more in the range of 1 to 10 megawatts per square meter. But to put that into context, the typical heat flux in a fission reactor for the cladding is only about 0.4 to 1 megawatts per
Jeez.
square meter. So a significant increase. that means that you're going to have very high temperature at the surfaces, but we know that most materials, just due to some of the effects that you previously mentioned, can't sustain that for very long. And so you have to cool these systems. But what that ends up creating is pretty significant thermal gradients in your materials and within your components. Something you might have a surface at 2000 degrees Celsius, and then you have coolant lines running at 100 degrees Celsius.
Jeez.
You may be even trying to get less depending on what your coolant is. That simply becomes a pretty big issue. That's a huge thermal gradient. And that's just an expectation based on what they believe these are going to be operating at. But many of these reactors, including the ITER, which is a large tokamak reactor being built in Europe.
That's the next generation of jet, which we've been talking about.
Yes. It's an experimental reactor. It's a research reactor. And so it's possible that you're going to have off-normal plasma operation scenarios that result in plasma disruptions or failures in the magnetic confinement or displacement events where the plasma gets much closer to the walls than anticipated. And so those are just other chance events that are probably within expectations that could accelerate some of these thermal stresses and the damage the materials are going to face. As I mentioned, there's going to be some off-chance events where you have your plasma in much closer contact to the walls than is desirable, especially in regions such as the diverter, which is used to extract the products of the fusion reactor in order to try to maintain the purity of the reaction zone. And, at such temperatures and extreme conditions, essentially what's going to happen is you're going to have these surfaces that are just rapidly reconstituted and altered by basically surface atoms being ablated and then resputtered on. So you're essentially going to have ablation of surface atoms and then redeposition of them. And they estimate that that's going to happen over 1 billion times in a single year for
my gosh,
some of the atoms on here. And not only can this just lead to odd structural formations on the surface, but you're going to end up with localized erosion based on defects in the microstructure of your material that will maybe cause some regions to ablate faster than others. And then you'll get redeposition and buildup in localized regions as well. In addition to that, in the act of sputtering, right, you have an exposed surface that's lost some atoms, and then you're going to those are going to be reapplied via essentially sputtering from the plasma, and that has the potential to trap tritium atoms within your material, and that means that you're actually taking away valuable fuel from your reaction, but now you're actually starting to store and entrap tritium within the materials themselves, which can cause damage.
Sure, I see. Yeah, so I mean, as if the thermal stresses and this plasma damage are not enough, the really big problem here is radiation damage, right? So radiation damage, in fact, there's a term that you'll encounter when you start learning about fusion materials or materials for fusion, is this radiation hardness. Radiation hardness, just like regular hardness, is sort of resistance to local deformation, like under indenting, right? Radiation hardness is resistance to damage due to ionizing radiation. And that can be at a component level or device level. And when you try to think of materials that are going to resist this, you first have to understand what goes on when radiation damage occurs. So you've got these neutrons that come flying into your material, and because they have no charge, they're not going to be repelled by the Coulombic forces. So they're not going to see an electron cloud and be repelled by it, which means that they can actually collide with the atoms and do so with really high energy. So they can have both elastic and inelastic collisions. But often in this terminology, they introduce this idea and this terminology of a primary knock-on atom. So the neutron comes flying in, and the first atom that it hits is your primary knock-on atom. Andrew, you've played pool before. When you break pool, what happens?
Yeah, I mean, balls go everywhere.
I mean,
it's not just the first atom. Excuse me. It's not just the first ball that you hit, but you get a transfer of energy.
That's right. And each one of those can then move and react with, the balls around it. The same thing can happen here. You might knock out one atom, which itself might knock another one out and another one out. And you can have, because these things come in with such colossal amounts of energy, you can have a bunch of different collision and damage events happening at the crystal structure, microstructure level, at the crystal structure level. So the types of defects that can form are really wide, right? For example, you can have the initial atom that gets knocked out might just create a vacancy. You're like, oh, that's not a big deal. But then where's that one going to end up? It could end up getting lodged in the lattice somewhere, right? So now you've got an extra interstitial somewhere. but more than likely it's actually going to cause a series of things. So you can have it actually ending up not in a nice interstitial spot, but right next to another atom. We call these crowd ions, right? Because it's crowded. You put essentially two atoms on very nearly the same spot. So these crowd ions can form. You can get the formation of transmuted elements, right? So in comes something, and then it can undergo a, what do you call that? We call that reaction, a transmutation event, I guess. You can get the
Sure.
formation of a transmutation event. So, for example, there's a problem in tungsten alloys. When they subject tungsten alloys to over 50 dPa irradiation, you end up with a mixture of tungsten and a little bit of rhenium. And the rhenium can change its properties quite dramatically. You also end up with some osmium, which changes it. So you might have had a material that you understood its mechanical properties, but now it's going to have very different, say, ductile versus brittle behavior because of these transmutation events that have taken place as well.
Yeah, and that's terrible from a material science perspective. You design and test components based on assumed properties, and now your material is transient. It's changing in ways that can be predicted, but are certainly not ideal. It's very difficult to test this.
And it's generally getting worse too, right? I mean, anybody who's taken an intro to MSc class knows that, okay, if you have this nice perfect crystalline lattice, everything's lined up just nicely, then it's easier for dislocations to sort of move through that lattice. That's the whole idea behind, if you've seen your blacksmith demo, they introduce dislocations, or if you do precipitate or solid solution hardening, you introduce atoms that are not quite the right size, and so it pins dislocations. Well, with that understanding, now imagine when you shot this neutron into a material and the atoms got all jumbled up, how much more difficult it's going to be for dislocations to move through that material. So generally speaking, you see embrittling, right? You see embrittlement of these materials, but that's not the only problems that can happen here. Another type of transmutation event can be the formation of helium, right? So you can end up with helium gas, which at first is maybe soluble in your material, but things typically have solubility limits, and this is no different here. In most of the steels, the alloys that you would be using in fusion reactors, they can only tolerate so much dissolved gases in them before those things will diffuse, come together, form voids, little pockets form within your material, and then that can lead to cracks and eventually failure. So they noticed this, I think it was in like the 60s, they first noticed that there was swelling happening in these things when they would irradiate materials, that they were technically swelling over time, and they realized that what was going on is that it was transmutation leading to these little gas pockets actually swelling the material.
Yeah, and swelling's a well-known phenomena for materials in nuclear environments, but it really is just the amount of energy here that's significantly higher than what would be encountered and experienced in a fission reactor. On the bright side, though, you do have higher temperatures, which, from a standpoint of resolving dislocations, is quite nice and quite helpful. But from the instance, as you mentioned, of void formation and migration of helium is quite bad. Higher temperatures generally mean faster diffusion. After walking through and explaining the pretty extreme environment within these fusion reactors, now comes time to actually look at the materials that they're trying to develop to withstand these and maintain them. So the plasma-facing components are naturally going to be seeing some of the most extreme conditions, right? These high neutron bombardment, high thermal stresses. And so, what are we kind of looking for there? Well, there's a couple key properties, these being thermal conductivity, strength, ductility, thermal shock resistance, thermal fatigue resistance, as well as low activation and general stability.
Oh, is that all?
Yeah, just a small list.
Okay, we're not doing like too crazy of multi-objective optimization here. Man, that's a
No,
lot of stuff
not
to
at
worry
all.
about.
Yeah, and I mean, it is kind of funny that, I think typically material scientists like to have quite a few options, but really the prime candidate right now is just tungsten and tungsten alloys, mainly because it has a very high melting temperature, a low vapor pressure, and pretty low tritium retention as well. However, it's quite difficult to machine and definitely suffers from some embrittlement. One of the other kind of big concerns with it is that we mentioned that it's going to be ablating and that tungsten atoms are going to be mixing with the plasma. Well, because of its really high atomic number, it ends up being quite detrimental to plasma ignition. It's basically an impurity. And so there's a lot of concern with direct surface reactions that are going to be taking place.
Okay, one of the things that's a kind of a pet peeve of mine is when people talk about, fission versus fusion or just nuclear energy in general, whether it's fission and fusion versus non-ones, is they'll sometimes say like, they'll point to all the waste that comes from fission, but then they won't say the same thing about fusion. But a lot of the fission waste, it's actually materials that are in support of the process and not necessarily the used fuel itself. So and they categorize these in different ways, right? I forget the ordering scheme, but it's sort of like the most severe one is the fuel, obviously, but then there's all these other ones. And that sort of approach doesn't always get taken into account with fusion, but in fact, you are now having a lot of irradiation. So you're going to have activation, right? You're going to have radioactive components that are coming out of these reactors, and they're having to take parts of these things out after their service life is done. And you're still having to store those things, whether it's a fusion reactor or a fission reactor. And that's not often included in the conversation, which is, I think, kind of not a fair comparison.
Yeah, I think fusion has been very much posited as a nuclear technology to try and make up for some of the deficiencies of fission. And really,
and they keep on pitching it as zero waste, but there's going to be waste here.
Yeah. And this has kind of prompted, I think, a lot of research into alternative materials to try to reduce that. So we mentioned reduced activation, like you said, materials that undergo interactions with the neutrons and end up undergoing radioactive decay events. But when we talk about a reduced activation material, what does that end up meaning? It ends up coming down to a lot of the elements that are going to be contained in that. So in conventional steels, for instance, you're going to have a lot of things like molybdenum and niobium and
nickel and copper
that are added to these. Yeah, and those need 200,000 years to achieve low-level waste criteria.
Yeah, that's not realistic.
Whereas reduced activation materials, these are going to be things where they're replacing some of these things like molybdenum with tungsten or replacing niobium with tantalum or vanadium. Those are able to achieve that low-level waste criteria after 5 years of fusion or radiation within about 80 to 100 years. So still a long time, but not nearly on the same scale as 200,000 years. And so that makes the disposal significantly easier, and also the maintenance of those disposal facilities easier as well.
Yeah, I think that's one of the big success stories of materials for fusion reactors is recognizing that you can take any materials engineer knows that stainless steel is this awesome thing. And so we just sort of put it all in one category, but we forget that there's endless possibilities in changing and modifying these things. And something that says maybe it has chromium or titanium instead of having nickel, molybdenum, niobium. You might have thought like, well, that just makes its properties a little bit worse. But if you can have a little bit worse properties in terms of mechanical properties at the benefit of drastically, 6 orders of magnitude reducing your activity timeline, that's a big win. And so I think that's one of the big wins that came out of this research in this area is realizing slight substitutions to the chemistry where you more or less retain the mechanical properties you're interested in or the corrosion properties, but now you've made a big gain on the radioactivity front.
Oh, yeah. But one of the problems still is that you're going to have an operating limit when using these sorts of materials. I think theirs is about 550 degrees Celsius, which limits the efficiency of your reactor. Naturally, the hotter you can get, the better. And so there's quite a bit of research into looking at other structural materials for these reactors, some of these being oxide dispersion strengthened steels. So these are just steels with nano-sized oxides within them, and these have the potential to increase the operating temperature by about 100 to 200 degrees Celsius, which may help you meet your safety factors a little bit better. These are, however, a little bit too early in development. One of the real big challenges I think here is that it's not enough to just say that a material exists. You actually have to have the supply chain to make it feasible to manufacture it on the scale necessary to build a fusion reactor. You can see papers all you want of people who arc melted a tiny little bead and did XRD on it, but how are you going to build a form?
Can you make tons of it?
Yeah. There's also quite a bit of interest in vanadium alloys. But once you start going to some of these other, maybe more exotic materials, you start to run into new compatibility concerns because at these temperatures, thermodynamic reactions that are maybe otherwise unfavorable or quite slow end up starting to become possible. Just because a material can withstand the thermal environment or the structural environment doesn't mean it can withstand the chemical environment.
Yep, exactly.
In addition to vanadium alloys, there's also quite a bit of interest in ceramic composites, such as 6-sit composites, in part because they have very good radiation resistance, little interaction with hydrogen, but they can also enable higher temperatures, going up to 1,000 degrees Celsius pretty comfortably.
There's something kind of cool when we start thinking about these for these applications. A lot of these plants seem to rely on blanket materials, right? These are either to protect you. If you've got these neutrons that are firing through the material, you need to absorb them, so you can put blankets on them to sort of absorb these things. And at first I just thought of these as just like sort of a protective mechanism, like, oh, okay, well, it's just shielding. But there's some really cool ideas out there on how you can use those combined with the irradiation damage events to actually generate fuel, right?
Hmm.
So these are called, if you've heard about tritium breeding materials, that's what these are. It's saying that, look, we know neutrons are going to fire into these materials, that transmutation events are going to happen. So what if you intentionally choose the materials that your blanket material is sort of made of to have things like lithium 6, right? And when the neutron comes and hits that, it can actually split that lithium 6 into two tritium particles, right? Or atoms. And that could be actually a fuel source because, as you mentioned, the best reactions are going to be deuterium plus tritium. We don't really have tritium. And this would be a cool way to generate it while also having the secondary benefit of shielding your overall reactor.
Yeah, I mean, the main idea behind them is that, well, let's see, we have about 20 kilograms in reserves. I think that's only enough for about a couple months of the ITER operating, which is not ideal. Our seemingly clean and limitless energy sources, we've run out.
Still stuck. Yeah.
Yeah, that ends up being a pretty big problem. And so breeding ends up being a way of trying to mitigate that and actually trying to not only create energy on site, but also create the fuel necessary on site as well. And so in order to try to maximize this, because with any sort of nuclear reaction, there is just like a probability of it occurring in the first place. And because the lithium's not directly exposed, there's quite a lot of possibility for neutrons to not necessarily make it there in sufficient quantity. And so typically you're going to also have a material for neutron multiplication. And beryllium's a really common one for that because it has one of the highest, if not the highest, neutron multiplication cross sections, which is just a way of saying probabilities.
Yeah.
More complicated than that. Where upon being struck with a neutron, the atom will fission, and upon that you'll get a production of 2 neutrons. You essentially double your amount of neutrons that could be then being used to produce your tritium. But one of the challenges there is that there's actually not that much beryllium out there. That's also a material in pretty low quantity. Most beryllium out there also has uranium impurities, which can be very difficult to remove. Beryllium is quite toxic, and it's not easy to work with. And so trying to remove those impurities, from my understanding, is quite difficult. And if you have those impurities, then you now start to run into the same problem with fission reactors, where now you have radioactive components that are going to last a long time in there. And so you start to run into the exact same challenges. And
Yeah.
so
In this episode, it sort of made me realize just how complicated, like, these things get sort of put out in the news and it's always oversold and it's always simplified. And when you get into it, boy, the devil's in the details. Like, there's a lot of materials advances that we still need to uncover before these things are going to go prime time.
yeah, and there is quite a bit of interesting design work and in both the mechanical and the material side going on here. I mean, to overcome some of these shortcomings with beryllium, there's a lot of interesting alloys that have been proposed. Rather than using a solid blanket material, there's more interest in using actually a pebble bed sort of structure, which is mainly to allow more surface area, but also for better release of the tritium, because once you produce it, it's still trapped in the
Right.
material. You have to get it
Right.
out. And if you do produce it there's also concerns about how do you contain it. Hydrogen is very difficult to contain, and tritium being just an isotope of that is no different. And so even if you can produce it, how are you going to make sure that you actually capture all of it?
Yeah. And if your answer to that is like, oh, well, we'll simulate it and figure out a way to do that. That's sort of our next topic, is that simulation in these materials is so not trivial. I think of what we've described. We've talked about picosecond, right, pulses. You've got things happening on the extremely fast time scale, all the way out to the time scales of creep over years, right? So you've got many, many orders of magnitude of materials interactions that you want to be able to understand. And it's also happening over big length scales, from the individual atom all the way out to components. And anytime that you're modeling across big time and length scales, it just becomes so difficult, let alone the fact that we don't necessarily have like calibrated models, because the energy of the things that are coming out of this are so much beyond what we've seen in fission reactors, that a lot of this is sort of unexplored territory from a computational material science standpoint, which isn't to say it's not useful, but there's a lot of work to be done there.
Oh, absolutely. I think there's a big problem with actually being able to characterize materials in the fusion environment. You know, it's, first of all, those are significantly higher energy neutrons that are going to be produced here, much higher than a traditional fission reactor, like you said. And so where are you going to go to actually test a certain material? There are some facilities that have popped up to enable this to happen, but it's not cheap. It's not like going to your characterization lab and putting something in the SEM or putting it in an instron or a load cell to try to test it. A single test can cost, tens, hundreds, even millions of dollars. And so how much information do you actually get out of a single test? How do you design it? What if you missed something? And so while there is a legacy of literature concerning some material properties, it might be that those aren't the right microstructures. It might be that there's impurities or aspects of the test that aren't necessarily related to the current applications and designs. And so, like you said, it gives you some information, but it's probably not enough.
Yeah. Well, we hope we haven't scared people off. In the face of all this daunting materials challenges that fusion faces, there's real opportunity for materials engineers to do cool things. There's companies out there working in the fusion space. My former PhD, Marcus Perry, he's working at Zap Energy. And today, actually, we're joined by a visitor to chat with us about this from Helion Energy. Okay, so with that background in the basics or the sort of Fusion 101, let's now talk about somebody who is actually trying to turn this into a viable business model. We have today with Claire Saunders, PhD, who is a fusion nuclear materials scientist at Helion. So all of you material scientists, I'm sorry, you're never going to get a cooler job than that. Fusion nuclear materials scientist. Claire, how are you?
I'm doing well. How are you?
We're super good. Claire, you and I met 4 years ago. I gave a talk at Caltech and you were a PhD student there studying, was it materials?
Yes, I was studying materials at Caltech and you came for the materials research lecture. And I remember we had lunch that day and you talked about the podcast.
So cool. And Claire has kept in touch. She sent some suggestions for episodes. And in fact, when the big fusion announcement came in December, we knew that we were going to connect and actually talk about this. Claire, how did you end up at a fusion company?
That's actually a funny story because most people are surprised to find out that I don't have a background in fusion or nuclear. And honestly, a year ago today, if you were to tell me I'd be sitting here talking about fusion, I'd probably laugh at you. The way I ended up coming to Helion was a bit of a roundabout way. And looking back, it's interesting because everything I did in some way prepared me for this role, but at the time, I had no idea. I grew up in a really small town in Northeast Pennsylvania, just south of a city called Scranton. Most people just know that place because of the TV show The Office.
Of course.
And growing up there, yep, I know everybody knows The Office. And growing up there, I never really appreciated how energy rich of a place it was. For example, I thought it was normal where my 4th grade class field trip took us down into coal mines. And we really got to see what it would be like to work down in a coal mine. And like a lot of people, my family had personal ties to the coal mining industry where my great-grandfather was a Polish immigrant who was a laborer in the mines. And he ended up dying from a disease called anthracosilicosis. So there's that level of connection with that kind of carbon energy that I've always had. And then I thought it was pretty normal, too, to grow up within the zone of a nuclear power plant. And I grew up within the close enough radius of the Susquehanna Steam Electric Station. It was a nuclear power plant, and I just thought it was really normal to have one of those around growing up. And I never really appreciated this, but at least I always loved science. And so when it came time to go off to college, I went off to Duquesne University to study physics and math. And I had an amazing time there doing research at national labs as well. One of the places I ended up was Oak Ridge National Laboratory, the spallation neutron source. And this is really where I started going more and more towards nuclear and fusion, but I just didn't realize it yet. And neutrons were really the connecting item. I worked at the spallation neutron source for a couple summers, and then when it came time to get my PhD, I decided I needed to go somewhere warmer because Pennsylvania was really cold. So I decided I was going to California, and I ended up at Caltech studying vibrational entropy of materials. And one of the ways to look at vibrational entropy is by doing inelastic neutron scattering. So fast forward, my PhD, I went through the whole thing, and I am getting ready to defend. And I see the job options at Helion, and they're looking for people that can really understand the behavior with neutrons and materials. And in all honesty, at first I didn't think it was a good fit, but it really turned out that the tools that I knew and used for thermal neutron scattering to look at vibrational entropy weren't that different than how neutrons interact with materials in a fusion setting. So that was a long way to say it was a really roundabout journey to get here, but I think it was pretty cool.
That is way cool. So in the introduction, we talked briefly about tokamak. We've talked about now the big breakthrough. And those have achieved fusion in very different ways, right? In one, it's using the 192 lasers, which do what they do. And then the other one, they actually have the toroid, which allows, I think they actually heat it both with radio waves and with neutron, right? So Helion, where do they land? Because these are two totally different approaches. What's Helion's approach?
So I always have to give the full disclaimer. First and foremost, I am a materials scientist. So my knowledge of fusion devices really is going to serve to enable me to solve materials problems. The things we can say about Helion's device, though. Helion, we're dealing with a linear device. It's in the shape of a cylinder, not donut-shaped like tokamak. At Helion, we do pulsed fusion, whereas in a lot of the tokamak devices, you're going to see it being steady state. And the interesting thing that we do is we use a combination of deuterium and helium-3 as fuel rather than deuterium-tritium reactions that you see in most tokamaks. And that's really cool from a materials standpoint because you get slightly different materials problems depending on how the machine is set up.
I was going to ask, what are those materials challenges and how are they different than what they're experiencing in the tokamak? In the introduction, we talked a little bit about the different kinds of fusion reactors and the kinds of byproducts you get. So maybe you can talk a little bit about how the specific reaction that Helion is using changes the sorts of problems you're dealing with.
Definitely. So with the setup we have at Helion is we're dealing with that linear device, and it's a cylindrical shape, and we're bringing the plasma into the center to meet. And so things that we're really concerned about are the materials that are directly around that because they're exposed to some pretty extreme conditions that you'll sometimes hear referred to as the first wall. And the issues in that area include things like temperature, they include things like fast neutron irradiation, they include things like hydrogen isotopes that we have to take into account.
So is the strategy to come up with a material that can withstand this long term, or is the idea to readily replace these things out in some sort of regular process, or what do you think is the right approach here?
So I think it's a little bit of both, because if we wait to design a material that can do everything, we won't necessarily get the engineering problems we want solved. So it's important to do a little bit of compromise, in my opinion, where we work with some materials where we know how they're going to fail and when they're going to fail, and then look towards the future as well in trying to design materials that will fail less often.
Yeah, that's interesting. Is it, in your opinion, it's better to go with what we have instead of waiting for research to catch up to the specific problems that the industry is facing? Because that seems to be what I see in the literature, is that tungsten seems to be a pretty good material all around, but it has some deficiencies, and a lot of work is going in to try to remedy those with alloying. But in an engineering setting and in a commercial setting, you can't really wait that long, because the time from a material's inception to being made viable for any sort of commercial setting is usually on the order of decades.
Absolutely. And I think it's one of those issues as well where we are seeing the effects of we see more effects from not doing things. And by that, I really mean that we're already dealing with a climate that's rapidly changing. If we just wait and try to make sure that the fundamental materials research catches up with what we're trying to do, it might be too late.
So what are some of the specific problems that you're looking at then? What sort of, in your day-to-day, what are the problems that you're trying to solve, and what are the ones that are particularly difficult and that Helion is particularly focused on with their technology?
I talked a little bit already about looking at neutrons and how neutrons affect materials. That is one of the bigger things that I'm looking at on a day-to-day basis. And that involves doing a bit of experiment. It involves figuring out what calculations to do and trying to figure out how long a lot of these materials are going to last. My role at Helion is really focusing on a little bit more of the longer term goals, because once we get the basic engineering figured out, we really need to figure out how long some of these materials can last in these generators. So I'm working on building different types of models, and I'm also trying to figure out ways for testing. And that's a lot harder than I initially thought it was going to be. And I definitely think it's one of those things where we have to figure out, what do we want to use more experiment? Do we want to use more computation? Because from a computational standpoint, ideally we want to use tools like molecular dynamics and really understand what's going on from a fundamental level. But that's can be pretty computationally expensive. And on the experimental side, it also just gets plain expensive, because doing irradiation experiments that are exactly like the flux that you're seeing in these reactors can get incredibly expensive. We're talking millions for a radiation experiment.
Plus, it's not necessarily apples to apples anyways, right? Because I know that a lot of the irradiation facilities, even if you match the flux, the energy of the neutrons is totally dependent on the reaction. And so your reactions may not be the ones that are represented in the experimental setup. So how do you know that you're actually testing similar conditions, since they can vary so much?
That's a major problem that we face, and we have to figure out what conditions are the ones that really matter the most. And I think this is where doing a computational approach or doing some kind of machine learning approach can really help us learn what's important, what's needed, and where to go from there. Because you're right, it's not a one-to-one, and at the end of the day, you're still making a judgment call.
I was just going to say, I'm always cautious when we think about using machine learning to extrapolate out to regions where we don't have data.
Me.
That sounds as ML, and who's a big fan of ML, I'm like, I don't know about that.
Because I really think it has to go hand in hand. I worked with a lot of people who always told me I would never be a good computationalist unless I understood experiment and complemented my computations with experiment. And I really understand what they're saying now, because it's terrifying. Extrapolation terrifies me, especially when you bring in some of the machine learning approaches.
Yeah, absolutely. When you do these sort of model first approaches, which anytime you're dealing with anything nuclear tends to be the direction you have to go, it ends up being quite tricky, because a lot of phenomena are generally understood in terms of material interactions with neutrons. And sometimes these are expressed in nice analytical equations, but the transition from an analytical equation to a numerical result ends up being pretty tricky. It's actually not trivial to simply take some of these equations and then add them to maybe an existing molecular dynamics or finite element framework. It becomes tricky. And you also go into this situation where you can use the models to figure out what parameters are important, maybe, assuming your equations are right. And so you can narrow down your experiment. But you always run this risk, like you're saying, with extrapolation, where your models could just be wrong and you're barking up the wrong tree. And with how expensive some of these tests are, you really only get one shot.
Yes. And it's a little bit alarming as well, because when I first started, my job was really to see how different levels of neutron irradiation, fast neutron irradiation, would affect different bulk properties like resistivity, thermal conductivity. And I was really surprised to find out that there weren't just wonderful equations that take you from point A to point B.
Oh, no.
And it was really based on a lot of experiment and some computation, but there's really not that connection. And I was surprised to find that out.
Yeah, what you'll get is you'll see a nice plot with scattered data and a trend line through it, and it'll be for a material that's completely different in microstructure than the one that you're using.
Exactly. I'm a big believer in microstructure before macro. And so for me, that's just incredibly scary.
So I've got a question. Is Helion in the alloy development business, or are you partnering and waiting for alloys to come along that might eventually one day be like the dream alloy for your application? Or are you just accepting the fact that things are what they are right now, and that might mean that you need to adjust things on the fly and change them out?
So this is a similar answer to what I gave before, but it's a little bit of everything there, where Helion at its core, we are an energy company. Our job is to bring zero carbon energy to the grid as fast as possible. So we're not a materials company. The way we use materials is to reach that final goal of achieving commercial fusion. So along the way, I'm looking at different ways to be a sort of proactive and a reactive approach to the materials design. So in some cases, I'll be able to propose, hey, we could look at this one material and it would be pretty useful for this setting. And in other cases, we're looking back and saying, okay, this material failed at this point in our testing. How do we respond to that? So it's in terms of developing new alloys ourselves, right now we're not at that point. but it's something that we're always keeping in mind, figuring out how to reach that final goal of having the generators on the grid.
Is this even realistic? Like the reason I ask is because you've got some of the biggest research groups on the planet that have been trying to do this for decades. The building is 10 stories tall. It's 3 football stadiums wide. It has 192 of each one of those lasers would be like almost the world's strongest laser. And they've got almost 200 of them doing their thing, right? Or tokamak and the new ITER that's coming out. Like, these are massive entities. How on earth is a startup supposed to compete with this? Is this, help me become a believer, because that seems really like a huge Goliath that you're up against.
It is. I think I would sound foolish if I didn't say it wasn't a big challenge. The way I think about it is that fusion is happening as we speak. We know that fusion itself works. It's happening in the sun and it's happening in the stars. It's happening. So the real problem right now is really that engineering problem. And over the past couple of years, there's been a lot more money being put towards these companies to really develop these technologies. And from a materials standpoint, I view it as we're really just trying to solve this optimization problem. And we've got to find the right candidate materials that can withstand the conditions and sustain this kind of reaction. I think I'm probably going to sound like a scientist who's the hopeless romantic, but it's like that idea that I want to believe in this. I think the theory is here. The theory is sound. And the idea that we can do something like this, I think we have to at least try.
Maybe going back to some of the materials challenges, there are a lot of neutrons and those can do damage to materials, but from my understanding, there's also a lot of transmutation events and diffusion-related processes that also pose a risk to materials. Are you looking at those at all?
We are looking at we're trying to see how all of the byproducts of our fusion reaction affect the materials. And I talked about neutrons already, but another big one is hydrogen and hydrogen diffusing in materials. And the issue with that is that it can make materials incredibly brittle. And the other thing as well is that our goal is really to make sure that we don't release amounts of tritium. Our goal is to make sure that we actually produce amounts of helium-3. And we're really trying to conserve those hydrogen isotopes and not let them damage our materials. And a cool thing for that is actually there's a lot of really cool coatings that are being developed for hydrogen permeation. And that's been an exciting field to learn about.
Can you discuss some of those?
Yeah, so it's commonly, I believe it's ceramics. I'm not an expert in ceramics, but there's a lot of development with ceramic coatings that make it difficult for hydrogen to permeate the barrier. And so if you don't get hydrogen actually going into your structure, you don't have the problems of the brittleness for the material. You do have the added thing where it is going to be a bit brittle with the coating because of the ceramic, but that's better than having your material filled with hydrogen.
Yeah, I mean, it's a tough problem there too, because not only are you getting all of these essentially Frankel pairs being generated by the neutron damage, so that's just opening up all sorts of pathways for diffusion. But from my understanding, there's also transmutation events that can happen within the materials themselves. Like you can be generating helium and hydrogen within the tungsten layer.
Yes, that is a big problem. And we pick materials with that in mind as well. So we try to make sure we understand what transmutations can happen before we actually run something or design something. And tools for figuring out the transmutations are a little bit more developed than some of the other tools. So in general, we have a pretty good idea of what some of these transmutations are.
But then how do you go about modeling that? Because essentially you just have I don't know if can you really use a continuum scale and just try to homogenize the effect of these defects? Or what does that look like?
So I've spent a lot of time thinking about this over the past several months, and I wish I had the absolute perfect answer. Ideally, how I see a lot of this going is developing these. I would love to see the models developed from a much more ab initio approach. And we're starting to see a little bit more of that, but it's a bit challenging, like what you're saying. It's not the easiest calculation to perform.
No, definitely. Once you get into that ab initio stuff, it becomes pretty difficult for industry to do that, let alone if you can find the expertise to do it,
yes.
Having access to the software to do it too, and then finding some sort of coherent theory for scaling those nanoscale simulations up to something that could be used in an FEA simulation, for instance. I imagine you're also looking at thermal loads on these materials though, right? You said that Helion's is a pulse reactor, so you should have pretty high rapid changes in heat flux. So is thermal shock a big concern?
Yes, thermal is definitely a big concern. And the fun thing I like about thermal, though, is that it's interesting how you can use temperature to modify some of the radiation effects, where if you heat to a certain temperature, you can avoid generating, say, like a number of Frankel pairs or something like that. So I've worked with temperature for a while. I've worked with my PhD thesis was a lot of just looking at how materials behave at higher temperatures. I think that temperature is actually a really cool tool that it's tunable to really try to minimize radiation effects.
The converse of that is as soon as you bring the temperature up a little bit, a lot of other reactions that are otherwise not favorable start to happen.
Yes, that is very true. And so with that one lovely solution where, oh yes, let's use temperature to affect the radiation, you do have that other problem as well. So it really is it's a delicate balance, and trying to find that optimization point is really where I'm at right now.
And so that is a really complicated problem. How are you going about trying to balance that? And what problems are you choosing to solve, and which ones are you choosing to not ignore, but solve at a later point, push to the side so that you can get the necessary results? Because a lot of what I found in modeling is it is about what you're trying to model, but it's also about what you're not trying to model. Because the more realistic you get, the harder it is to get converged solutions, and the harder it is to actually accurately represent it. You start introducing more error.
Yes, it's really figuring out what can you work with, what can't you work with. And I really view it as, I keep saying, this optimization problem where you've got experiment, you've got theory, and you've got computation. And any problem we tackle is going to fall somewhere within this like triangle of these things. And so you're trying to strike that balance between cost, efficacy, things like that. And so it is heavily dependent on, number one, data that exists. Do I need to run experiments? Are there calculations that have been done already that I can use? And so it really ends up being a case-by-case basis, which I don't know many other fields that are like that right now, because we're playing catch up as material scientists in fusion, because now that we're getting closer to actually solving the engineering issues, we have to refine a lot of the materials. And so it's really trying to leverage what data do we have, what computation do we have, and how can we use that to either develop more data, develop machine learning models, or just really trying to solve this big problem.
And how useful is some of the legacy data that's out there? Because fusion's been around for a long time, so from my understanding, there is a decent body of literature on fusion materials. Is it just very scattered? Is it maybe too focused and not broad enough? What's been your experience?
It's very specific to the reactor that's being used for some of the tests. And I find that some of the data is more relevant than others as well, because depending on the energy of the neutrons they were able to use for it, where at Helion, most of our neutrons are going to be 2.5 mega electron volts, whereas for some of these studies, it's going to be 14 or 0.1. And so you're really trying to figure out how does the difference between what I'm trying to look at and what they're trying to look at affect how the properties change. So it's definitely, the field has a lot of data, and I do appreciate that. And another thing I truly appreciate is that all of the people who went along the way and developed the neutron cross sections, those guys were awesome, because looking at those, I'm like, this is a lot of data to really figure out, and without those, we'd be completely lost. So in some areas where we're pretty well set with data, where we could do like basic envelope calculations. In other cases, though, we're using it as a guide, and we know that we can't trust it completely because our setup is different.
That's got to be tough. And so,
It definitely is.
And you mentioned that Helion's not really a materials company. So do you imagine you're going to have to contract a lot of that out? Or do you think Helion's going to invest in characterization equipment to do this internally?
So it's really going to depend. I think those decisions really depend on what our goal is at the end of the day. And if we have a goal that we need to figure out quickly in-house, that's going to necessitate an in-house approach versus an external approach. The cool thing right now is that there's a lot of contractors, vendors popping up who are developing really cool business models to help with the fusion industry. So you're not at a loss to find people to help you solve these problems.
That's good at least.
Yeah.
What do you think isn't being worked on? What are some of the things that you've started to discover as being maybe problems or issues where there just isn't enough data? If someone's out there, a researcher who's keen to make an impact, or someone who is trying to figure out how they can contribute, what isn't being worked on in your eyes?
I think the first thing that we really need to start working on is, it relates back to way in the beginning where my title, Fusion Nuclear Materials Scientist, it's a mouthful, but there's not really a lot of training to become a fusion nuclear material scientist. And it's hard to find people who have that right balance of understanding the materials enough and really understanding the nuclear component enough. And it really struck me that this was a problem where I was in a meeting with my manager, and he mentioned that we're trying to find another material scientist, and he said that we needed to find a generalist like myself. And having a PhD, I think it just I did not like being called a generalist. It felt really strange to me. I spent how long of my life really specializing in a certain area. But then I realized it's like, this is actually a good thing, where you can jump into a problem and solve it based on whatever tools you have. So I think one of the first things that we'd need would be training more material scientists who can really fill these roles that are going to keep popping up, who can really jump in, and you could put them in the lab, you could have them do computation, a little bit of everything. And I think that would be incredibly helpful, because right now it's a lot of just people learning on the job as they go.
Yeah, and I remember when I was a grad student in Taylor's lab, I TA'd a few classes, and one of them was a Python course. Material scientists haven't done a lot of computation in undergrad. It seems to be shifting, and that's a good thing, but I remember always getting groans from students about, oh, why do we have to learn this? Or I'm never using this again once I get out of here. And it was always like, once you get into the industry, you're going to be solving really tough problems. In fact, I think the problems that I've had to solve since leaving school are much harder than the ones I had in school. And a lot of that is having more tools at your disposal, because none of these problems are going to be set in stone. There's not going to be a guide on how to solve them. And if you don't have access to certain tools, maybe you don't know how to run an experiment or what an experimental design would look like, or if you aren't able to develop computational algorithms or even code to help you speed up analysis or do analysis you couldn't do in Excel, then it just limits the kind of problems you can solve.
I completely agree. And I would say as well, this might catch me some heat from the experimentalists, but I think the idea of having people who are entirely experimental scientists, where they don't go on computers, they don't do code, I think that in some ways is dying out. And I think it's because we're seeing that coding and computation are they're tools rather than an end themselves. Really, anytime I'm working with a student, I encourage them to pick up some kind of programming language, because that's going to really be something that helps them along the way.
Okay, it sounds like Helion is looking for material scientists. If there's anyone in the audience listening who wants to become a fusion nuclear material scientist, where should they go?
So you definitely check out the website, helionenergy.com, and we have our job applications there. And like you mentioned, we're currently looking for a material scientist. And other places to check out what we're doing at Helion, we have a great YouTube channel, and there's a lot of great videos that have been made about us recently. And I'm also starting a LinkedIn group for people who are focused on fusion materials. So if you just look up fusion nuclear materials on LinkedIn, you could find that there as well.
Awesome. Hopefully some people reach out to you, and hopefully that gets off the ground. There's a lot of interesting problems to solve in that space, and it's going to take a lot of brains.
It definitely will.
All right. Thanks, Claire, for taking the time to talk with us. I think this is a great episode, and we're looking forward to hearing what you do next.
Yeah, thank you for having me.
See you around, Claire.
The Materialism podcast is sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the materials science field and read some of their fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
Thank you for listening to this episode of the Materialism Podcast. If you've got any questions or feedback, send us an email. Actually, this episode today we did because Claire wrote us and said, hey, I'm a fan. I love your episodes. We've got to talk about fusion in light of this big announcement. We agreed. So reach out to us. We're easy to get a hold of. You can find us at materialism.podcast@gmail.com, or we're actually much more engaged on Instagram and Twitter. So our Instagram handle is @materialism.podcast, and you can connect with us there. We also post lots of fun pictures and additional stuff about the show, some behind the scenes things. So check us out there. It would really, really help us if you would leave us a 5-star review on iTunes, Spotify, Google Play, wherever you listen to your podcast. Leave us a positive review, and it will help us expose the show to new people. That would be really great. Finally, we want to give a big shout out to Alphabot and Kolobyte. They're the ones who make the really cool music that we use in this podcast. So thanks to them. We think they make good stuff, and we think that you should support them. You can find their stuff on Spotify and YouTube. So with that, we will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.